If I could choose one fact for you all to take away from my speech here today, it would be that a group of bunnies is called a fluffle. For the past 2 years, I have been studying the mathematics behind animal group formation, which means for the past 2 years, my brother Matthew has been listening to me talk about the mathematics behind animal group formation. So when Matt started his undergraduate degree here at UOIT last September, he decided to try his own experiment. One day, while moving between classes, Matt realized that a group of his peers was moving with him. He responded by taking a purposely convoluted route to get to his next class, and was delighted upon arrival to find that he was still surrounded by a group of somewhat disgruntled students. What moral can we take away from this story? Other than the fact that my brother will probably have a very difficult time making friends here. Animals naturally want to be in groups, so they take cues from their neighbors in order to form them. A single student who shows up late to class is far more likely to be singled out than a group of students. Similarly, an animal separated from a herd is far more likely to be eaten by a predator. Anyone struggling to see the similarity between these two situations should try being embarrassed in front of a first-year class. The cues that animals take from their neighbors are heavily dependent on distance and tell an animal to move towards, away from, or in the same direction as a neighbor. For instance, if an animal is very close to his neighbor, he will move away. If an animal is very far from his neighbor, he will move towards him. Only when the animal feels he is a suitable distance away from the neighbor will the two align and move together. This concept of attraction, repulsion, and alignment regions has been used greatly in one-dimensional models of animal aggregation. But these models limit an animal's movement to either left or right. By extending the concept to 2 dimensions, you get a far more real-life applicable model, as an animal's position can now be expressed as an angle from 0 to 360 degrees and by an x and y coordinate. The complication that comes with extending the model is that it becomes increasingly difficult to solve. While some initial conditions allow me to solve the equation by hand, others leave it near impossible. Because of this, I've been working on a series of computer programs that allow me to use time stepping to solve the equation. For any initial condition, the program tells me the number of animals facing in any direction at any given coordinate in the domain at any time. Ideally, I would like to use this information to create a realistic visual simulation of animal aggregation. Thank you for giving me the opportunity to speak to you about my thesis. Hopefully one day, with the help of math, we will be able to better understand the elusive travel patterns of first years and fluffles.